Hello, allow me to continue where I had left off yesterday. Both my apologies and also what they call accepting reality that this EMI EMC shielding has a tremendous, very wide both the implication and theory and practice. So, theory has been developed such that probably along with the communication and along with radiation and along with antennas and all. So, if you look for a simple search on the internet, you will find tremendous amount of data, and also there are textbooks and textbooks and textbooks. And on the other hand, the actual practice has been going on parallelly, saying somebody has been developing gasketing, somebody has been developing windows, means that small openings through which you have to take things, and this also has been going on very in a parallel course. Like so many other things, sorry for being judgmental here, practices continue irrespective of whether the theory is developed or not, whether it is fully understood or not. So, on the other side, by using simple reducing things to manageable level, theory also has been developed, and now with computation and all, with a reasonable prediction, they can make out how to solve problems. And because of the complexity, any number of firefighting design services are available, so that they can implement the theory and then the practices they have been following for a long time. So, you to have given an example of how at home, if you are an audio enthusiast, you will see that hum is real. It could be 50, 60, 100 or 120 hertz hum. And if you touch somewhere, there will be something, and then grounding also is real with respect to this hum and noise. This apart, somewhere we have to make a beginning that we should start. So, I started this is where I would like to apologize, saying, am I reading out from commercial trade what do you call literature? Yes and no, because it is more like a white paper, and somebody has got down to it and written things in a concise manner with examples and partly taken from probably Tom White's book and partly taken from their own field studies. So, in all this, I will get back you to for this thing which I left yesterday. So, you see here finished requirement for structural metals. So, we have this saying, no, what type of coating and all you give, and then it seems to be common compatible coating seems to be this chromate passivation or chromate conversion. As you go down, this each company has its own trade name and compatibility. So, you see here the first group 1 talks about these various things, including gold and silver and so on, and all the way down you have magnesium and tin and all that. With each of these groups overlaps, making it possible to safely use materials from adjacent groups. So, the issue being here is that depending on the type of materials we use and depending on type of contact surfaces we use, when plate something here has to make a contact, this is where the dissimilar materials thing come, and as if it were not sufficient, we have the problem of moisture and other, I will say, electrolyte type chemicals in the atmosphere. So, it in everything forms a nice cell. I have given an example of how nickel cadmium batteries are made. So, obviously nickel and cadmium do not go together. So, kindly read it with me here. So, we have here big list of chromate conversion coatings, iridite, and can be considered as this thing, and then they have given from their own characteristic this thing, saying we try to conductive urethane coatings. This coating sticks to the surface where you want to make a seal, which is a very positive thing. So, they have given here saying no. I think if you remove all the double negatives and all, not enough. Actually, a lot can be said about surface preparation. Need to be said about it. So, they have given about how much and so on and so on. Smooth to the touch when cured, recommended that the coating be cured at room temperature 2 hours, followed by their thing. No, it probably it comes to around 120 degrees centigrade, 1.5 hour whenever alternate cure cycles are available, and so on and so on. The thing is, all this have been developed saying how to apply these materials. So, you have here saying corrosion potentials of various metals and EMI gasket materials. So, we have this if you take silver plated, copper and so on and all that, aluminum filled elastomer, copper and nickel and so on, we have a large number of numbers like this. So, I suggest you read up more about it. What is galvanic corrosion? For galvanic corrosion, a unique set of conditions, two metals capable of generating a voltage, electrically joined by path and immersed in a fluid capable of dissolving the less noble of the two, an electrolyte. In short, the conditions of a battery must exist. This is exactly what a few sentences ago I had shown you. So, whenever you have any of these two things, you have a liquid which forms the electrolyte, and then you have two dissimilar metals. It is almost like a battery. So, you know what happens. When you do not want it, it will become a battery. When you want it, it does not. That is the reality of. So, there is something called the galvanic potential. But in spite of it, a caution has been given here. Tables of galvanic potential do not accurately predict the corrosivity of the metal filled conductive elastomers because of the composite nature of these materials. These tables do not measure directly to important aspects, saying corrosion resistance, the corrosion of the mating surface flange, and so on and so on and so on. If you go down, you will see that huge amount of data is generated. Allow me to move on to the next slide. So, like all other, including IP67 tests for immersing something for long periods, and also for drop tests and all that. There is no simple easy way to predict behavior. Chaotic. I have told you the joke about raining on my picnic. So, either way we have a problem. If I carry an umbrella, it won't rain, so looking funny. If I do not carry an umbrella, it will rain, getting wet. Same thing in the case of this EMI also. After the EMI, all the precautions are taken. Everything is tested using test fixtures like this. You understood? So, lot of stuff about how the weight loss is there over the time, how corrosion takes away the material, and so on like this. So we have this very important thing. Corrosion control by and large presents the same problem whether the gasket is silver filled, monel wire filled or tin plated. Furthermore, a designer must understand the factors which promote galvanic activity, strive to keep them at safe level. It should recognize some corrosion is likely to occur. So seal to seal and so on, non-conductive, so on, huge amount of data is available. And then here pictures are shown of the test results. You see around the edge where it is exposed to the atmosphere and it can get all the necessary moisture, you will see that it has corroded all around at the edge. The center does not seem to be so bad. Comparison of corrosion from chosil and pure silver filled elastomer with aluminum. This, well, I will not say it is not real, it is individual case specific. Individually case specific. Every time minor variations including the clamping pressure, including the ambient conditions, we have this problem. So we have this class C tests, and if moisture is expected to reach the flange interfaces in class C marine, flange surfaces should be coated to make them more compatible with EMI and so on and so on. There is a huge amount of how to deal with all these situations. So if you move on a little to the right side, you see here the correct pressure and how much of deflection is allowed in these things, because that is a very critical thing. It is down somewhere here because it is a PDF file. So I have to need to go back. So you see here, fastener should be located such that pressure distribution is uniform at the corners, groove designs and so on as you go down. Okay. So you see here, gasket deflection ranges have been given, saying typically things like this, solid, very small, and you see here especially thin ones, negligible, it is only 25 microns. However, you have a lip like thing which makes it more flexible, it is hollow inside, will have the advantages better this thing for a 5 mm build up, you get a tenth of a quarter inch, small thickness like that. Hollow gasket configurations are useful when large gaps are encountered or where low closure forces are required. So again, if you remember IP 67, so if you remember IP 67, you need to apply force on all the sides. If this were to be a thing that needs to be sealed, obviously you start with 1, 2, 3, all this, almost like an automobile crankcase. Large forces are allowed, but you can't do it every time. If you have a simple power control panel like what I was showing you, you can't afford to take a ring spanner and tighten everything, or in fact use a torque wrench and tighten, because there are some issues about frequently being, you should be able to do it, and then doing something like that is expensive. So invariably they have large gaps or where low closure forces are required. So low closure force means you just need to shut and then turn one lever and the thing stays in place. That is what I had shown you on the outdoor camera there. So hollow gaskets and tabs in the text and tables are referred as P gaskets because they are little like that. Minimum wall thickness of hollow this thing is at about 0.5 millimeters, and then up to typically 1 to 2 millimeters it will be there. So there are compression limits also, saying a compression stop should be provided. In the next coming few pictures, they will show you saying if this has to meet here, it is not just enough if you put a little bit of gasket here. You have to make sure that you cannot squeeze it. That is what the table talks about, saying you put a stopper to ensure that beyond that it can't be squeezed. And then so we have this stuff about manufacturing technology, how do you die cut and so on. So based on this, exactly because of this, when I told you about, it is a specific, case specific, meaning every time we need to find out how the things work. So we have here saying depending on how well the tolerances are held during when you blank them out, fully mold them, or when you punch them out, or you have an extruded strip. Okay, die cut gaskets and so on. This is more a detail of the see here, this is what I was talking to about. So you have forces and how do you thickness and all that. I will just go through quickly. Now you see here that it is just not enough. You have pressure sensitive adhesives and how to attach it. Friction fit in a groove. So some of you who enjoy or who have watched people cooking using a pressure cooker, you see all the pressure cookers come with a gasket. In these parts of the country it is common, and we can't afford to have very hard gasket in which you tie things. I am sorry, you have wing nuts or all the sides or levers and you clamp it with large force. That is only used in places like our laboratories where we have autoclaves and then we have vacuum and we have pressure and all that. All other places you have just a split gasket like this, small gasket. It sits on two things and then you close the lid and then you slide the lid and we expect it to stay in place. It is okay, it does not matter. A gasket probably costs 50 rupees or little more than that. I will call it a $1. So you can change it once in a while. In fact, I am one of the persons who keeps a spare gasket at the first sign of any leakage or any movement which is too smooth. We discard the old one and then start using the new one, which is probably quite a bit to do with, you have seen this, no? We have adhesive, non-conductive, spot bonding and friction fit in a groove, and you see any number of robotically dispensed form in place conductive elastomer. You would have seen this as your caulking which is used for windows. You have the RTV compound, room temperature, vulcanizing, some rubbery material. Advantage of it is for quite some time is expected to continue to be soft. It should not become hard. If it is hard, it has some problems. So just before the arrival of winter, probably people seal all the windows with this, with the window sealant, and afterwards they will peel, remove all the accumulated dust and other stuff, and then we are back in business. However, in the case of professional equipments, it is not that easy. Means once you keep it in place, until something functionally fails, it is unlikely that you will ever attend to this in a periodic way of replacing the gaskets every time. However, to prevent, generally people have a little this thing, so routine inspection is carried out to make sure that especially water borne or underwater, IP 6768, somebody examines it whether they are cracking in the all the elements here. So we have here friction fit. Friction fit means nothing but just push it and then it squeezes itself on that, on the edge of the enclosure. Then fully customized integral conductive elastomer, plastic spacer and so on, blah blah blah, All this stuff is available from multiple manufacturers. So, it is for you to decide what you would like to have, and in this you have clips to hold it in place and so on. If I get a chance, I will try to show a Faraday cage we have on our premises. I need to access it by taking permission. There you see that all these, what all have been done here, have been taken care of. So, we have all this nice slowly we are coming back to applied force. Most applications do not require more than 100 psi to achieve an effective AMI seal. So, you have a gasket, it has to be pressed hard. Anything more than that, as I said, no, as they have indicated, it is likely to damage it. Anything less than that, tangential forces can come and corrosion can also start. Somewhere an optimum saying around 50 to 70 psi, that is area square inch, and then we have all this. This is fortunately, no, this equation does not look so threatening, saying how much does the flange deflect, fastener sizes, spacing. As a general rule, should not be spaced more than 2 inches for stiff flanges, more than 20 mm for sheet metal if high levels of shielding are required. The moment you leave any gap, at the time of installation there is no problem, but the slightest deflection or slightest change, often caused by temperature with combination of changing in humidity, will compromise the bonding, continuity and connection between them. So, that is the reason I will see if I can get some pictures before the video. So, we have our Faraday cage. So, that in the cage, when the door is closed, all along with a pitch of 15 or 20 mm, there are fingers which make a continuous contact top to bottom, and after some use that fingers have a tendency to set. So, somebody comes and I think once you are allowed to align it or something, afterwards they replace it. And the important thing is that you must conduct a test every time. Like if you have a balance, let us say you need to take a weight of something, you do a tear reset. Same way, whenever any professional tests and all are required, before they start the test, they also try to make sure that the whole equipment is calibrated. So, other than that, the chances are, so here now they have given examples of saying how to calculate the bolt spacing in case you want and all that. I think you can read it yourself. I will give you the link, and otherwise the material will be available. So, you can easily find out about the error factor, spacing and all that, actual deflection and so on and so on and so on. And we have a little problem about waveguides. Waveguides are again a very, very special case of this thing. It is not connected with this at all, except that all I would like to say is any slightest error, you may completely lose your signal. So, the what do you call the UHF, I do not know, microwave thing does not go at all inside. But you see that these have been compounded or something by other way. So, all that plumbing gets seriously affected in case we over tighten things and all that. So, there is a lot of little more theory, and shielding effectiveness versus pressure and so on is given like that. If you apply more than certain pressure, it does not improve the shielding in any way. Understood, no? I will leave it here on 2 counts because it is not immediately relevant to our packaging, and secondly, I am no expert at it, but it is for you. And most of these companies give you enough what do you call, data, background data on how to continue with this. This is a 200-page note. So, in order to produce a gasket in a groove which will not fail and so on, no, you see huge amount of data has been given. This I thought, no, why I was going about is, you see here, this is an interesting thing. Now you will notice exploded view of an electronic enclosure. In this case, because of because of the ease of analysis and because ease of illustration, they have taken an enclosure which has a nicely milled flat flange. Similarly, there is a cover, though it is not seen here. Very rarely a cover will sit directly. So, just under that, this much part which is mating with this also will be milled clean. Make sure that it is level. So, it is probably kept on a special clamp on a milling machine, and a small finishing cut is there. Then after this, if you now try to clamp things, and then this green is a gasket, see here, so you have bolt spacing, and then you have an O strip, conductive elastomer in a rectangular groove. You see, small errors can happen here, lack of conformity. To avoid this lack of conformity, they try to give the milling cut, so that generally they sit together. There is only in extreme cases this can be done. If you recollect in the video, I was trying to show you the water cooled inverter. I do not know whether it is called an inverter or a drive, where because of the high current density, we have actually water pipes running inside the electronics. In spite of our using good, I will use the word good coolant, we still have issues. Most coolants still have a problem. If it is a pure good water, obviously water has the best specific heat. Anything else you do for improving some other thing, including the boiling point, including the antifreeze, including everything, part of that conductivity comes down marginally. How well it can take away heat from the adjoining parts. And coupled with this, any of these inequities, we end up with flooded something. I have already talked to you about how flooded gasket, a failure in a gasket ends up with a flooded crankcase. So, your water ends up with small leakages will be there which go into a crankcase, and these will get circulated. And the normal cases there is no problem, because once in a while, I think routinely you check these things. So, as you go down, you see you have this beautiful thing, where the bolt is spaced, where its full force is there is okay, but in between we have the problem of things failing a little. So, further I will go down. Maximum gasket diameter, minimum groove depth. So, you see here, these are simple cases by which how you will pack a gasket in a groove, but these are a matter of detail, and if you are to design any of these things, most likely it is enough for you to sensitize yourself that such things exist. You will not be an expert in it, because first of all you have to locate the materials, find out all these practices. Secondly, after populating or packing the whole thing, you have to ensure that you put it through some tests. So, these are all part of the testing thing, and how if you overpack it, chances are, see, there is a little bit of creep which has set in here. In this case, nominal groove width, it does not matter. So, we have so many of these nice pictures and all. Maybe this flow chart give you an idea. You see very clearly, there is no automatic converging set of rules which will pick one of them. It's still, I won't say completely trial and error and completely what do you call blow something and find out. It's a little to do with iterative, saying select start with something and then build on it. So it's given here saying select a reasonable gasket diameter, calculate groove depth, establish tolerances. Here is the problem. Normally most of this gasketing, if it is molded, it will come in a fixed size with probably some blister pack. In the blister pack, they will probably include already some adhesive if it is not come with it. Sometimes it will be dry powder, sometimes it is a wet this thing, and then if it is a round or a square, no, it is usually folded and packed such that it sits nicely. So a circle, no, if you fold it, you can reduce the whole thing into a 1/4 of the diameter, but it will end up with 3 or 4 things. So once you open it, somebody has to measure the thing, saying are these valid, the tolerances. Especially something which is stored, both things can happen. Gaskets swell, they become bigger than nominal, and also they become brittle, and sometimes they shrink. Shrinking in the thickness is not so bad, but shrinking in the overall material, the whole size does cause a problem, which happens in the case of the cooking gaskets. If you start with an 8-inch, yeah, I think 8-inch looks big, 200 mm is big, probably they are all 180 mm. A worn gasket, you will notice that it would have shrunk by about 5 millimeters, and then just that 5 millimeters is sufficient for it to be absolutely unusable. So here you talk about gasket deflection, minimum gasket deflection, formula 3, calculate nominal groove width, verify that final groove dimensions satisfy both minimum and maximum deflection and groove fill limits under worst case tolerance conditions. This is for only calculating the groove dimensions, but I said it is a professional specialist job. Normal electronics people need not worry too much about it. So there are so many of these formulas, and fortunately these formulas are easy to use because next level of maths is not involved. There are no integrals, no differentials, no summation, no matrix multiplication and so on. Oh, we are coming into porous region. So far they were solid, though the elastomer may have some small cells inside, either open or closed. We come to a very nice interesting thing, is a mesh gasket. Any advantage of a mesh gasket? To start with, overall weight is less. Secondly, again going back by the original theory, the amount of, depending on the frequency, the lower the frequency, the smaller the holes are there. Higher the frequency, I do not know, I am not able to make out. All I know is 2.5 mm is sufficient for 30 megahertz, which was the earliest communication designs I have done. So you see that the advantage of a mesh is they can be spaced close together, and if you just pack an area with it, overall the amount of material content is small. The moment material content is small, because a mesh is made of wire string, you can use the highest quality material, and during the manufacturing they have perfect contact. Reasonable example is your coaxial cables or even shielded wire which you use for audio. Seen that, no? It has a nice braid like this, crisscross braid. Imagine the same braided thing but much more closely controlled and much more thicker. So you have crisscross thicknesses of not just one, maybe a dozen layers and so on. Here what they have done is mesh strip gasketing. The use of mesh strip with elastomer core provides additional resiliency. Little problem with the earliest thing is that if something can be made porous, chances are it may not do the thing properly. What do you call it? The function of isolating or shielding, it may not done properly if it is very porous, and it is very dense, it is not flexible anymore. So they have tried to give here, and they have given with all these things, saying what is packed with. Obviously inside is where the mesh is there. This part is the other what you call backing up thing, which can be held together. So things can be pushed inside. Then we have a simple non-conductive adhesive is sufficient, and subsequent pictures will show you more and more about. So you have the mesh portion itself can be punched. You have the mesh portion that is punched. It sits properly, and you see here then large amounts of specific cases on how to take care of most cases. So you see here there are gaps, unwanted gaps are there, there are gaps, there are places where things touch each other. So we can see here rivet or spot weld strip or mounting fin, okay, so on and so on. No? Large number rivet or spot weld aluminum extrusion to cover our cabinet, okay, door. It's a little like, is it not common sense? Of course it is common sense, but in the rush of things or something, or trying to concentrate on other thing, chances are we'll miss it. It's a little like proofreading. When you write first time, I don't think you can really read what you have written. So you notice that if somebody else reads it, he'll notice that it doesn't seem to sound well. Forget idiom. Normal typos or the full expansion of the printer's devil comes in. Same thing happens in the case of these. How we implement small detailing while the doors are closed, and how we implement small detailing about how to clamp things. Yes, it is a lot of common sense. In this case, common sense being tried and tested method as compared to hit and miss. This is obvious, I think, and you can see for yourself when you try to close the door on the top section. There is a mild amount of rubbing after it hits, and in this case it compresses automatically. While in this condition this rubbing is considered bad, some other conditions it is considered desirable. Whenever you are trying to make a pressure contact, which I shall connect in which I will repeat in the connectors class, butt and wipe seems to be the best way of ensuring contact. So even in the case, in case that something is not used for some time, a little bit of corrosion or something forms, if you touch something and then now squeeze it, that surfaces get scraped as connected, as compared to a simple silver button in a contactor which keeps going but like that, millions of operations. But in the case of our industrial connectors, the 3-pole and 4-pole which we use for our machinery and all that, we have a completely metal clad enclosure. So something goes inside and then a slight amount of twist is given. The twist has double advantages. You have a bayonet holder and then something scrapes here. So from that point of view, in this case they are saying door slides on EMI gasket. So it is for you to take a call on it, saying would you want it to slide or not. So depending on the material, depending on the chances of corrosion and all that, no, and how frequently do you use. The problem is, if you want to put it into this corner, it's not easy. This corner it looks like, no, it's relatively easy. So we go on mesh gasketing materials. So we come back to knitting. Knitting is, it is woven, we have a knit and purl like this, a series of gammas which are there, and the next one goes into it, and that's how knitting is done as compared to a simple mesh cloth. Knitted wire mesh can be produced which can be drawn into wire form. Great majority of shielding requirements are satisfied with the choice of two materials, monel or ferrex are standard production materials. Two design required shielding, required corrosion resistance of the gaskets. So you see here, two things are given here. One is monel, the all purpose nickel copper alloy resists oxidation, maintaining its conductivity, good EMI qualities, and very good mechanical strength and resiliency. In controlled or protected atmospheres, it may be used in contact with aluminum also. Where can we see this? Next time you get a chance, anyway, don't destroy anything, because it's not like one of that popular TV science series. Have a look at your microwave oven. That front glass, you'll see a small, a cover with small openings. That is the one that ensures, in the unlikely case with all the internal reflections, a ionizing radiation doesn't get out. Ionizing the one is the one that causes burns and suspected to cause cancer and so on. Non-ionizing, it's fine. I don't know the difference, but let me leave it at that. And then all along where they mounted, because that itself, it's either a sheet which is punched carefully or etched in that case, or it is a coating directly on the glass. The way this is attached to the outside panel is where you are likely to see this. Similarly, when you close the door of the micro oven, one of the things is you have a gasket there. I expect that at least some of these things are taken care of a little. I cannot vouch for that, but thing is the total exposure time and all that, I think the largest cooking may be around 25 minutes to half an hour. Typically everything is the order of 3 or 4 minutes. And two other things you will notice, it's very different from the refrigerator gasket. The refrigerator gasket has some other function. In this case, both it has to seal against the heat and steam that can escape from inside, plus ionizing radiation. So typically you are likely to see all this. So ferrex tin plated copper clad steel wire offers the best EMI performance. Leave the commercial or trade notices, most of them know, with undisclosed manufacturing process. We have these materials. There are, I think, as I see now, about a dozen major manufacturers are there who give all these gasketing materials. Other than that, lot of contacts are there, finger contacts and ferrules which will go and make contact here. For low frequency magnetic field shielding, recommended are ferrex versions of knitted mesh. High frequency electric field and so on, first best corrosion resistance, because moment you have gaskets, we have all this. So we have large number of commercial, they are listing in the catalog. It is again 2-3 things. One is how do you attach or assemble to your various parts. Another is how effective is it in the shielding. So you need to worry only that part about it which it is there. So I will just go through quickly, hopefully. Oh, we have so many of these things, woven wire and elastomer and huge this thing is there. I will see if I can rotate it clockwise. So, you have the trade names and characteristics and so on, and of course, there are tested and proved certifying agencies which guarantee the whatever claims they have made. You have seen here, important thing is this EMI ratings, mill STD 285 is only a test method. It does not guarantee, or it is not a normative procedure saying something should have this much. But if you specify whatever measured values are all reported there. So, you have all these various products, and like just like mill STD, because these are all have evolved from military applications, you will see that often cross reference is given to them. But when that thing was going on, what you call, when the standards and all were being prepared, it was a little to do with how testing was carried out, so that it is field deployable or field worthy, not so much as the analytical part. Probably analytical was also carried out, but because of the speed and all that, it was done by practice more than preaching. So, later on I think it moved to the academics, and we have all this. So, we are almost coming to the end of the, I will say, book reading session. Okay. It just mentions what all I have, degradation and so on and so on, conductivity, mechanical, abrasion, resilience. So, my own suggestion for you is, kindly go look at this particular thing saying EMI shielding theory and gasket design guide from Chomerics by companies, that name also is given, Parker, I think it is called Chomerics or Chomerics, I do not know, and read this book. I mean, it is just a note, it is very small, it is, the full thing is around 300 pages, but this section is only around 120 pages. I find it authoritative with both design guidelines as well as a little bit of theory which is backing up. However, if you give a simple search, you will find multiple hits. So, yes, I thought I will anyway, next one I will try to do. See, this particular hearing aid what I have is the in the canal hearing aid what I have. Earlier we had a problem with trying to converse on the phone with it. So, earlier behind the ear, and then the pocket hearing aids used to have what is called a T-coil, telephone coil system. So, inside the hearing aid there is a small pickup which magnetically picks up whatever is provided in the that hearing what you call telephone. Old telephones were based on a magnetic speaker. You have a coil, and then very surprisingly there will be a strong magnet inside. I had to contact somebody in the communication industry who explained to me why it is. You also check up what it is, why the magnet is needed, and then you have a disc. The thing is, whenever any voice is excited, I mean whenever voltage excites the coil, you get the sound, and then the stray magnetic field is enough for the hearing aids to pick up these things. So, they were all built with a T-coil. Then subsequently it was found out that while it is a blessing in some conditions, it is not such a big blessing in all conditions. So, there used to be a switch, you can switch on or switch off the T-coil. If any of you are about my age or already suffer from loss of hearing, or as somebody says, no, failure to pay attention when people are talking. You look up on that. Okay. So, thank you. I will take a, I mean, I will stop it here, maybe we will continue in the next thing. Meanwhile, I will try to go to the that place where the pictures are for EMI room and see what best I can do. So, thank you.